Hi, everybody. So today's session is with Dino Peran from University of Split. He will speak about normal forms for logarithmic transseries.
Okay, thank you. I want to thank the organizers for letting me participate on this seminar and this program. So today I'll be talking about some part of my PhD thesis. So I done my PhD in December 2021 under the supervision of Tamara Servi and Maya Resman. And today I will be talking about our joint work with Maya Resman, Jean-Philippe Roland, and Tamara Servi. Okay, just to mention that this research of mine is fully supported by the Croatian Science Foundation and by this other grant. Okay, and let me just mention some papers. And here is a link to my thesis. Okay, and the content of my thesis mainly coincides with the content of these four articles. So first one is published, and the second one and the third one, they are submitted, and the fourth one is in preparation. Okay, so today I will be talking about, mainly I will be talking about this this article. Okay, so today I will be speaking about differential algebra of logarithmic transseries. I will define what is a logarithmic transseries, and then I will be talking about some topologies on differential algebra of transseries, and I will define the composition using, of course, these three topologies. Then I will explain what we consider to be a normal form. Normal form is so the problem of finding a normal forms naturally appears in dynamics. So in this formal setting, I will explain what it means for some transseries to be a normal form of some other transseries. Okay, and then I will talk about the main result about the linearization theorem. Okay, let me start. So just to mention that we are working with the formal variable z at 0. So it's not a variable at infinity. It is often convenient to work at 0 when you work some dynamics. So we decided to, since our motivation comes from dynamics, we decided to work with the formal variable at 0. Then you formally define the L1, and inductively you define Ln. Okay. So what is element of this space Lk infinity? It's just the formal sum of these terms. So you have real coefficients, and then you have some monomial, which is a formal product of power and logarithms. And this tuple, this set of tuples form a well-ordered subset of this set with respect to lexicographic order. Okay, it's often very convenient to write f like this. We call it a blockwise notation, and we call every R alpha a block. It's a block in L because what you do, you just fix one power, okay, and then you just consider here R to be a transseries only in logarithm. Okay. I will go through some notation. So this is notation for a coefficient. Okay. which is attached to this this tuple. And what is the order of F? It's just the minimum of the support. You can take minimum because it's well ordered. So, what is a logarithmic transseries? It's such an F that its order is strictly bigger than 0, 0, 0, k plus plus 1 times. Okay, so obviously LK is a subspace of LK infinity, and we call it a space of logarithmic transseries of depth k. So we have a fixed depth. Okay, so you fix k, and then you consider logarithmic transseries of depth k. So you have a fixed depth. What is order in Z is just minimum of these exponents. Okay. And you have the derivation in the usual sense, monomial. You just derivate monomial by monomial. Okay, so we have obvious relations. So these LKs forms, I think it's often called a tower of vector spaces. And you take the union of all LK and you get the differential algebra of all logarithmic transseries. Okay. So what about antiderivative? So we proved the proposition. So if you take this element of LK infinity and you try to integrate it, of course, without the constant here, you end up in the larger class. So you increase your depth, but in any other case, you remain in the same class. Okay. So let me talk about some topologies on the space on the differential algebra of logarithmic transseries. First of all, we have a usual valuation topology, which is defined using some metric that we often call a power metric. So how to define a power metric? You just take two logarithmic transseries. Let me just go back. You write F and G blockwise, and then you compare the blocks. And you take the first block that is different. Okay, and it's well-defined metric. So in this topology, we call the valuation topology. Second one is a product topology. So it's L with this topology is in fact Tikhonov space. So what it means, that this sequence converge to this logarithmic transseries. So you take any, so this bold M is in fact M1, M2, MK. So you take any tuple and you look at the coefficients. And if these coefficients converge in a discrete topology on reals to this, then you have a convergence in product topology. So basically, this sequence of coefficients have to stabilize in some point. Okay. And the weak topology is basically the same thing. Instead of discrete topology on every coordinate space, you just take Euclidean topology. So obviously, this topology is weaker than a product topology, and the product topology is weaker than valuation topology. So, but they are different. Okay, let me just go through some counter examples. So, for example, if you take this sequence of logarithmic transseries, this converge in product topology to this transseries. Why? Because if you fix some tuple, it's not a tuple. Here you just have only powers, so it's some number. Then you get your coefficients here stabilize at 0, and here the coefficients stabilize at 1. So you get this, and it diverge in evaluation topology. It's of course easy to see because evaluation topology is finer than product topology. So suppose that this converge in evaluation topology, then it should converge to this. But it's easy to see that this is not the limit of this sequence with respect to evaluation, because as you go further, your distance, so let me just use my pen, your distance is this. Okay, and it goes up to this, but it should go to 0. Okay, so it obviously diverge in evaluation topology. And the other counterexample is so this sequence converge in the weak topology. Why? Because when you fix some member of support, then you get the sequence that converge here, that converge to 0. So you have 0 times z plus, of course, 1. So you get the convergence in a weak topology, but it diverge. Sorry, this is a mistake. This is true, but this is not the point. It diverge in even in product topology. Why? Because this does not stabilize. Okay, and the last example, which is not a counter example, it's just the example of a sequence that converge in evaluation topology. So you get here some partial sums. This is irrelevant because as n goes to infinity, this is bigger and bigger. Okay, and of course the limit should be infinite sum, and this is well defined because your n is increased. Sorry, this is a mistake. It's not n, it's I here. Okay, and here is I. Okay, sorry. So this is well defined logarithmic transseries, and it converges in evaluation topology. Since it's the finest topology, then it converges in product and the weak. Okay. Unfortunately, this set of all logarithmic transseries with respect to our power metric, with respect to, of course, our evaluation topology is not complete. So we restrict ourselves on spaces LK. So if you have a fixed depth, then your space with respect to the power metrics is complete, but whole tower is not complete. Okay, the counter example for this, you just consider a sequence defined like this, and it's easy to see that it's not it's Cauchy, of course, but it does not converge in L. So if you take how to see it, if you expand this space, and you allow your depth to vary, then it's easy to see that the limit of this sequence is in fact infinite sum here, but it's not an element of space of logarithmic transseries. Why? Because your depth should be fixed. Okay, and this goes to infinity. So okay, so this is a counterexample, and we prove the proposition that every space LK, when you have a fixed depth, it is complete. Okay. There is a nice connection between the notion of summable families and product topology. So if you take any family in LK, which is countable, then it is summable if and only if this sum converge in LK with respect to the product topology. Why is this? Because if this family is summable, then when you take this infinite sum, then for each coefficient in this sum, there should be only finitely many n's which participate, so to say, to compute this coefficient. So it's when you fix some coefficient, it is enough just to take into consideration only finitely many phi n's here. It basically means that your coefficient, after some finitely many steps, stabilize in this series. Okay, so it means that you have convergence in a product topology, and vice versa. So it is in some problems, it's very nice to have maybe topology and to speak about the convergence in some topology rather to speak about the summable families. Okay, and this second thing is a direct consequence of the first, because if you have a summable family in LK, then you have a convergence of this in a product topology. Since product topology is finer than weak topology, then you have a convergence in the weak topology. So it's obvious. Okay, so let me talk about the composition of logarithmic transseries. Our main goal for the definition of composition is that our space LK should be closed for the notion of composition. Okay, why? There are several reasons, but mainly because our space LK is complete with respect to power metric, but L is not complete. So obviously, if you want to define composition in the usual sense and you try to compose, for example, L1 with L1, you get L2. So you were in class L1 and you end up in L2. So obviously, you cannot define the composition in the usual sense on whole LK because your composition is not closed. Sorry, your space is not closed for the composition. So you have to restrict yourself to some smaller subset of LK. So we define the set of all transseries, of all, of course, logarithmic transseries in LK, such that they don't have any logarithms in their first terms. Okay. So we distinguish among them. We distinguish the three types. First type is parabolic. So they are parabolic if they satisfy this. This HOT means higher order terms, lexicographically. Okay. And hyperbolic if they are of this type and lambda is not equal to 1. And strongly hyperbolic if they are of this type and your alpha is not equal to 1. Probably the motivation from this for this classification comes from dynamics, complex dynamics. So there are some. I will not go into details because this is not the topic of my talk here. But if you are familiar with Koenig's theorem and Fatou theorem about the classification of analytic diffeomorphisms at 0, then there you have a same classification. So that motivation comes from dynamics, so you have a first term without the logarithms, and then you can use Taylor theorem formal Taylor theorem, to define the composition. You take basically any f. So f can be any element of LK. But the second one should be element of this restricted subset. Okay. And then you just take a Taylor expansion. So this is in the same class because there is no logarithms. This is in the same class, and then you have obviously multiplication, which is closed, and you get in the same class. But here, the problem is how to make sense of this sum. So it can be proven that using Foy-Neumann's lemma, that this sequence forms a summable family, and then you have a convergence in product topology. Okay, even there is even more stronger result. There's even stronger result if you take G. So if your G, sorry, if G starts with Z alpha plus something, and so on and so on, then your increase, you have increase in powers here, and you get a convergence even in stronger valuation topology. Okay, so we define the composition, and we can ask ourselves the second question. So can I take any initial part of this transseries, and can I expand it for any initial part here, not just lambda Z alpha? Yes, we can, and we prove it in this proposition. So you basically, F is any element of LK, and G is element of LKH. And you take any initial part here, and you take G1, and you can expand your composition like this. So this first part goes here, and this converge in product topology, and even more if the order in Z of this is strictly bigger than alpha. So if it starts here with something bigger than alpha, then you have a convergence in stronger valuation topology. Okay. So it is obvious that LKH with such a defined composition is a group. And if you take all parabolic logarithmic transseries or depth K, it's a normal subgroup of this group. Okay. So let me just talk about normal forms. So we let me just recall you what we did so far. So we defined what is differential algebra of logarithmic transseries, and we defined the three topologies, and we defined the composition, and have a result about convergence of that sum in Taylor expansion in product topology, and under some additional assumptions in stronger valuation topology. So we have a composition on our group here. So usually in dynamical systems, what is a normal form? You want to conjugate some system to another system which is simpler in some sense. Okay, and you take the simplest one, and that is your form, a normal form. So what to do here? You just want to formally conjugate original logarithmic transseries to a simpler one. What it means, simpler one? In our setting, it means to have as less terms as possible. So you want to kill as much terms in your original logarithmic transseries. So that is our goal right now. Okay, so on one hand, you want to simplify a logarithmic transseries. Okay, but you have to have some conjugation, which is obviously element of LKH, but maybe it's this group is too big for conjugations. Can I take some normal subgroup, and then, for example, if you take only parabolic conjugations, you get a normal subgroup. Is it reasonable to have say axiom that your conjugations should belong to LK0, should be parabolic? I don't have so much time to go into details, but for me, the motivation for this restriction comes from dynamics, from the Kenning's theorem, from the Fatou theorem, and so on. So there, the conjugations are parabolic, because you have what is parabolic transseries. It's almost identity. It's identity plus something very, very small. Okay. Okay. So what is our problem? We want to solve this equation. This equation, when you have a fixed f, okay, so your f is some element of LKH. So if you remember, it's a logarithmic transseries of that k without the logarithms in its first term. This is fixed. And this is an equation in two variables. One variable is a conjugation, and the other variable is a normal form. You don't know in advance what is your normal form. So you want to kill as much terms as possible, but you don't know what you can kill, what you cannot kill. Okay. So there should be some result which indicates what you can kill, and then you try to solve equation with your best guess what should be a normal form. Okay. So in my dissertation, in our papers, we solved the above equation for any this is not correct, for any f which belongs to LKH for any k. Okay. But for simplicity, because I have my time is limited, I will talk only about the hyperbolic f. So let me just recall you what is hyperbolic f. It's a logarithmic transseries of this type. Okay, and lambda is not equal to 1. Okay. Okay. So we first proved this result. Okay, if you take hyperbolic f, this equation can be solved if and only if G is of this type. What is F0? F0 is a sum of all terms in F of order smaller than or equal to 1, 1, 1, 1, 1. Of course, I will explain later on some examples what is in fact F0. So what is crucial here at the moment, that we found conditions for G such that this equation can be solved. And we have if and only if here. So what should be our normal form? It should be F0. Because we cannot kill anything inside F0, but we can kill all of this. Okay. So a hyperbolic logarithmic transseries can be linearized. What it means to be linearized, of course, it means that it can be formally conjugated to G when G is linear. So it's basically lambda z. If and only if this F0 is lambda z. So it is a direct consequence of this this result. So in the sequel, since this should be our normal form, we just set G to be F0. So we don't have an equation with two variables anymore. We have a candidate, good candidate for F0, and we have equation in one variable. We want to solve this equation for parabolic phi. Okay. So let me go through some examples of F0. So if F is an element of L1, so the order of this term, sorry, okay, the order of this term is 1, 1, 1. So it should belong to F0, but any other term is of the order strictly bigger than 1, 1. So we can kill everything else. So this is our normal form. If you have this f, hyperbolic f, then this is 1, 2. It's strictly bigger than 1, 1. You don't have anything in between. So your normal form F0 is lambda z. So in this case, you can linearize this hyperbolic logarithmic transseries. In this third case, this is of order 1, 0, 2, because it's an element of L3. 2, 0. Then, of course, 1, 1 minus 1, 0 is strictly bigger than 1, 1, 1. Here you have 1, 0, 1. Still, it's smaller. 1, 2, 1. So this is bigger than 1, 1, 1. Strictly bigger than 1, 1, 1. So I can kill this, I can kill this, and everything rest. So this is our normal form. So what is interesting here? It is interesting that if you consider L0, here you have only power series without the logarithms. You can linearize any hyperbolic element of this set. If you move to L1, then you have two types of normal form. One type is, of course, lambda z, so those you can linearize. The other ones are lambda z plus some a z l l1. Okay, it's not ideal like here, but it's finite normal form. So it's finite. But if you move in L2, then possibly you can have infinite normal form. For example, I can write it. For example, if you have lambda z plus z, and then you have some here you have n goes from 1 to infinity plus something. All this stays inside your normal form. So it's something that we did not expect, because if you move from L1 to L2, you don't expect such problems and such complicated normal forms, but it is as it is. Some normal forms here are infinite. Okay. So let me just go back. We want to solve this equation with our candidate F0 for normal form, and this is fixed, and this is a parabolic logarithmic transseries of the same depth. Okay, so let me talk about some ideas and approaches how to solve this formal conjugation equation. So one approach was done by Mardesic, Roland, Resma, Roland, and Jupanovic in 2016. So what they did, let me just write some transseries. for example, some lambda z plus zl1 plus z squared, and so on. So what I did in their paper, so obviously you cannot kill this term. So you want to kill, for example, this term, then you take some, they call it elementary changes of variables, which are parabolic, and then they conjugate f and kill this term. Okay, then you maybe add some new terms here, and then you have to compose to another changes of variables, and then you kill another one, and so on and so on. So you get also with transfinitely many changes of variables. So you have to define what it means, what is a transfinite composition. So I think they used some of these three topologies. I think maybe I'm wrong, but I think product topology, but maybe I'm wrong. But it's certainly some of these three topologies. Okay, this is for me it's okay method, but the problem is that it's very hard to control the support of the conjugation. Okay, and your algorithm is transfinite. So in our work, we wanted to find conjugation more direct. We wanted an algorithm which is not so to say very transfinite. And the ideal technique for this is to consider some fixed point theorems. So if we can define some operator, which is a contraction in some complete space, then you get your conjugation as a limit of Picard sequence. So you have a nice algorithm how to compute the conjugation, and it's not so hard to control the support of conjugation. Okay, so let me just introduce some convention from now on. So for the sake of simplicity, in this talk, I will restrict myself on the simpler problem when F0 is linear. Why? Because the techniques when F0 is linear and when it's not are pretty much the same. But if you take arbitrary F0, the details, there are a lot of more details and the things are very technical, but our idea is pretty much the same as if you take linear F0. So from now on, your F0 should be linear. Okay. So first of all, our motivation for such transformation of the equation to some fixed point equation comes from the famous Koenig's theorem about linearization of analytic diffeomorphisms at zero. So if you take hyperbolic analytic diffeomorphism at zero, there exists a unique parabolic diffeomorphisms which conjugate f to something linear, of course. So how is done? You just consider this sequence, and it is proved that this sequence converge uniformly to conjugation. Okay, so there are two questions that we want to answer using this theorem. So we want to transform our conjugation equation to some fixed point equation, and then we want to prove that a suitable operator that we will define is a contraction. Okay, and this should be just a Picard sequence. It should be limit of a Picard sequence. So let me just define what we called Koenig's operator. So you take any parabolic transseries of the same depth as f, and you define operator like this. So basically, you just divide this by lambda. Okay. So let me just expand this using a Taylor theorem. So this f goes here, and then you have h composed with f. So you can write f. You can write f, of course, as f minus lambda z plus lambda z, and this lambda z by Taylor expansion goes here and here, and here you have f minus lambda z. So unfortunately, this PF is not a contraction on the space of all parabolic transseries with respect to the metric dz. Why? Because of this. So there is no increase in exponents of powers here. So it's an isometry. So we tried to come up with some new metric, maybe, such that PF will be a contraction. But we defined in our papers, we defined what it means for metric to preserve the order. I will not go into details, but the general idea is as you go, so as your order increases, you should be you should be sorry, my mind just blocked. You should be your distance. I'm older and older, so the distance between 0 and your transseries should be smaller and smaller. Okay, as you go, as your order is bigger and bigger. So that is what it means for a metric to preserve the order. Okay. So why do we want that our metric preserve the order? Because if this transseries start with something that is bigger than 1, for example, if it starts with z alpha and alpha is strictly bigger than 1, here you have increase in your powers. Okay, so your order should increase up to infinity as you go further. Okay, and your metric should preserve the order. But we proved that there is no order preserving metric such that PF is a contraction. So maybe there is some, I don't know, artificial metric such that PF is a contraction, but there is no intuitive motivation to come up with such a metric. So you have you can solve this problem two ways. One way is to change the operator, and the other way is to come up with some new metric. But obviously, it's a lot cheaper to transform this operator. So instead of considering this equation, we will consider this equation. Okay, so let me just go slowly step by step. So let me just write what it means PF of ID plus H. It means when you take the Taylor expansion, you get this. Okay, and then you cancel identities. You put this on one side. Okay, and you put this on the other side. Okay, so you transform your equation and you get a new equation, S of H equals to T of H. So So what we did so far, we transformed the original conjugation equation to a fixed point equation, and then we transform it again to a new fixed point equation. So we started to, why this is interesting? Because this is an isometry, and this is a contraction. Okay, if of course this starts with something, with some exponent in z, which is strictly bigger than 1. So this is a contraction, this is isometry. So we started to look for some fixed point theorem with some assumptions that can help us to solve this equation. And we found the Krasnoselski fixed point theorem. Of course, the Krasnoselski fixed point theorem is proved on a Banach spaces. So you have to have a norm. We don't have here norm space. We just have a complete metric space, and our metric is not induced by norm. So we cannot use Krasnoselski fixed point theorem, but we started to look in the proof of this theorem, and we realized that we have even better assumptions than those in Krasnoselski theorem. So we proved our theorem, our fixed point theorem, which is not a consequence of the Krasnoselski fixed point theorem, but the idea of proof is based on the proof of that theorem. So let me just define what is homotopy in our setting. So you take any coefficient here and let x and epsilon be metric spaces. So a map T is a homotopy if it preserves a metric up to multiplication by some coefficient. Okay. So let me, so the proof of this theorem, of this fixed point theorem, is very easy. So I will explain it here. So you have space x and epsilon. Here you have t, and here you have s. Okay. So what is t? T is lambda homotopy. So it means that it admits an inverse. Of course, not from epsilon in general, but from but from its image t of x. Okay, sorry, just this is let me just erase this. Sorry, somehow I cannot write here. Okay, so you can right now you can define the composition. Why? Because the image of S inside, it's inside the image of T, and you have inverse here. And since you have this inequality, you get that this composition is in fact a contraction. And since our X, space X, is complete, then you can use a Banach fixed point theorem, and you get a fixed point of this operator, which is equivalent of existing a unique point X, such that this equation, it's a solution of this equation. So the idea is to use this theorem in this situation. Okay, so what we did, so you take any f, okay, and you let your beta be order in Z. What is order in Z? It's a minimum of when you consider all exponents of powers of this transseries, okay? And you set S to be this and T to be this, okay? So this is an isometry. So it's basically one homotopy. And so this is fixed. So it's completely irrelevant because this does not depend of H. So you consider only this. And since the order is beta and beta is strictly bigger than 1, you have here increase. And as a consequence, this is a 1/2 contraction. And then all assumptions of our previous theorem are satisfied. So we basically solved this equation, and immediately we have a solution of the conjugacy equation. But there is another problem. What if beta equals to 1? So if beta equals to 1, this is not a contraction anymore. It's in fact one Lipschitz map. I don't know if it is an isometry, but it's one Lipschitz map. So we don't have this inequality because this is one homothety and one Lipschitz. So we cannot use this proposition. Okay, so the idea in this situation is to pre-normalize our original transseries. So what it means that if your f starts with lambda z plus z and some else here, some monomials in L, and plus, for example, z squared and so on, higher order terms. You want to get rid of this. So in your pre-normalization, you kill everything here, and then you end up with a transseries, which is of this type. So it means that you have lambda z plus higher order blocks. So for example, z squared, z to the power 3, and so on and so on. Okay, and then in this form you can use a previous procedure, because there is anything inside the first block, your beta is strictly bigger than 1, and you can use previous procedure to kill everything rest, and you can linearize your transseries. So let me just talk quickly about the pre-normalization. Pre-normalization is a bit technical, and in order to explain it, I have to define what is a space of blocks. So instead of considering all transseries, we should consider only transseries with logarithms, without powers. Why? What is the intuition behind it? So it is because we want to kill everything inside the first block. These powers are irrelevant, and you have fixed power here. And the only thing what is important are L's here. And the second reason is obviously our metric dz, which counts exponents of z. It's not very strong to distinguish an increase in L. It can only distinguish the increase in z. So we have to define what is a differential algebra of blocks, and then some metric on this differential algebra, and try to solve the equation in the setting of blocks. Okay, because powers are irrelevant. So what is BM? A set of all such transseries. Okay, what is order in LM is just the minimum of the set of all these exponents in LM. Okay, and you define new metric BM on BM in the same manner as DZ. There you just count powers, and here you count the exponents of the LM. Okay, and it can be proven that this space BM is complete. And we have a derivation on this space defined like this. So there are two reasons why we define the derivation like this, not just this, because this derivation defined like this is a contraction in our space. And the other reason is, I don't have time to explain it in more detail, but it's very well synchronized with the usual derivation. Okay, so there are two reasons why to define it like this. Okay, and there are some three subspaces of the spaces of block. One space is a space of all blocks here with order strictly bigger than 0, and the other is of order of those who are of order in LM strictly bigger than 0. And you have nice decomposition here as a vector spaces of this space when you take one. And why this is important? It will be important later. I will explain why. So we want to, sorry, do I?
You're a bit over time, so you should conclude so that we can.
Okay, sorry. Okay, so remember, we want to solve this prenormalization equation. The idea is the same as before. We just want to transform it to some fixed point equation and then use our fixed point theorem. But here Q is a block, not a general transseries anymore. Okay, and then we prove some. We prove that S0 is contraction, T0 is a homotopy, and what we need to prove is that image of S0 is inside the image of T0. And how we prove it, we transform our equation to some non-linear differential equation. So this is a derivation, this is linear part, and this is non-linear part. And we use this composition. So remember, this equation is not linear. So we decompose the equation, then we found a solution inside this space. And then we carry this solution inside this space and then find solution and carry on. And we find solution inductively in space B1. And that is why this decomposition is very, very important. So basically we can solve this nonlinear equation using this decomposition and our fixed point theorem. Okay, so I don't have time to give a solution, to give an answer to one more question, but you can read it in papers. They are available online. Okay, and just one quick remark. An application of these results to some problems in dynamics. I'll be talking about it in mini workshop on transseries and dynamical systems. It starts next Monday. And this is the second part of my thesis. And thank you for your attention.
Thank you, Dino.
Okay.
Are there questions or comments?
Now, Jean-Philippe wants to ask a question, but
I think it's okay right now.
Is it better? Do you hear?
Yeah.
Okay.
I can hear you.
The question is the following. I suspect that the answer is probably no, but I wanted to check with you. So here in this work, so you are taking a logarithmic transseries which belongs to LK, and you are looking for a normal form under conjugations which also belong to LK or LK plus 1. Am I correct? If you allowed yourself big possibilities for conjugation, that is conjugations in any LP or LP, would it be possible to obtain a simpler normal form or not?
No, unfortunately, no. We proved it that only what we can improve is if you. So for hyperbolic transseries, there is no improvement if you take any LP. For strongly hyperbolic either, because every strongly hyperbolic normal form for every strongly hyperbolic is basically first term. So you cannot improve this anymore. But for parabolic, if you take parabolic f, then you cannot kill the residual term in LK. But moving from LK in a larger class, you can kill even the residual. But moving in some LP, there is no improvement anymore, I think. So you can, there is only improvement if you move from LK to LK plus 1, but only in parabolic case.
So the only improvement you could make that way is to kill the residual term, right?
Sorry, I didn't hear you.
Sorry.
I'm buzzing.
So the only improvement you could make is for parabolic transseries, and the only thing you can do is to kill the residual term, right?
Sorry, I cannot. There is some microphony, or I don't.
Okay, so.
Yeah, I think, do you hear me? I think Jean-Philippe asked is the only improvement in the parabolic case that you can kill a residual term in one class bigger and nothing more than that.
Yes, yes, it is true. You can kill only the residual.
And it doesn't happen that you would need so it happens just in LK plus 1.
You can kill it in any bigger class, but why to go inside a larger class? It's enough to consider only LK plus 1, because every other class has inside this LK plus 1, so you can kill it.
No, but it's enough. You don't kill him. You don't generate something LK plus 2 and then need another, and then it's like
no. Mm-hmm. Okay.
I have another question. Is it possible to adapt these techniques to the case where you could take real powers of the logs?
We are working on it currently, but there is a hope that this can be done with not so much effort. So I think we can easily adapt it.
So if it were the case, maybe this will help to treat the case of general grid-based transseries.
I don't know answer right now for that question, but I don't know.
Yeah, might be tricky, I guess. Yeah.
When you take, there is quite a problem with exponentials. So if you take, if you want to adapt this method, then you take even exponentials, not just logarithms, and then there's a lot of problems with exponential. But I have hope for for such improvement. Not maybe huge improvement, but some small steps.
Thank you. Any other question? Okay, let's thank the speaker again. Stop the recording.